in class, we introduce this term transformation, which is just the same as function. It's just a fancy term in linear algebra. So now the next stuff that we want to do is to actually take a look at kind of like visualize some linear transformation. Okay, before we actually look at this 3x3 matrix, sometimes it's good to take a look at one-dimensional or two-dimensional stuff so that you have some good idea on what transformation really means. We'll begin by looking at one-dimensional case. So in one-dimensional case, 1D, you just have a real line, real number 9. So this is what you have, -1, -2. And your matrix should look like 1 by 1. So it's 1 by 1. Let's make an example. Say suppose this is 2. And your x should be also 1 by 1, because in order for a times x to be defined, these two numbers have to match, right? So x is any real number. And let's look at its effect. So ax is actually 2 times x in this case. Now, if you look at the effect, 0 times 2 is going to be 0. And 1 times 2 is going to be 2. So 1 is going to be moved to 2. And 2 times 2 will be 4. And -1 times 2 will be -2. So basically what this does is, so this 1, after multiplying 2, it's moved to here, right? So this point is moved to here when you multiply by 2. So this point 1 is shifting to the right and then becomes 2. And -1, in this case, it's shifting to the left by a factor of 2. So now therefore this becomes -1. And 2 is multiplied by 2 is gonna go to the original position would be 4. So in this case, 2 actually goes to where the 4 was in the last number line, and -2 will go to -4, right? So oops, sorry. So this means -2 goes to the where the -4 was. So this is the new location of -2. So the effect is basically just stretching your number line by a factor of 2. So this is one example. Now name another example. Suppose a is, say, -1/2. So what will that do? So I'm gonna create another new number line here. So in this case, if -1 multiplied by -1/2, it actually is equal to 1/2, right? It goes to here. And 1 times -1/2, it actually goes to here, -1/2. And 2 times -1/2, it actually travels to this point. And -2 times 1/2, it's traveling to this point. So as a end result, this line, actually you are gonna rotate, flip it, and then condense by half. So therefore -1 goes to here, and 1 goes to here. So this -1 goes to here, 1 goes to here, and -2 goes to here, and 2 goes to here. So that's what the effect of this -1/2 does. Okay, so that's what this actually does. So basically you flip it and condense. That's what it is. Now maybe another way to look at what this does is think about this arrow. Think about, I'm gonna, on the original number 9, I'm gonna make an arrow. So this is the vector 2, vector 2. After this transformation here, so the vector 2 becomes vector -1, right? So this vector 2 becomes the original vector will go to this place. So after that, this is its image. So this would be this guy would be the image of this guy in this transformation. So that's what this in one-dimensional what transformation does. Now, what about in two-dimensional? So I'm not sure if I have covered enough material or not, but I feel that it's good to show you some examples so that you have some idea what this transformation actually, what some transformations actually do. So in two-dimensional, so you have, say, suppose this is your 1, this is your 2, this is your 1, this is your 2, and so on and so forth. So you can imagine there are a lot of grid lines in your xy plane, right? And okay, now say suppose you look at this vector, which is 1, 0, right? And then also look at this vector, which is 0, 1, 0, 1, 1, 0, 0, 1. This is one example of two-dimensional transformations. Okay, I spent quite a bit of time to sketch this one, but here's the thing. Suppose we have a transformation A, which maps this 0, 1 into this vector. So basically, if you look at that, it seems like this transformation change this 0, 1 vector into some vector like this in here, something like this in here, right? Okay, I need to delete that. I don't want to ruin this picture here. And then also this transformation change this 1, 0 vector into a vector like that. So it's kind of like stretching and then pointing down. That's what this effect is. So after the transformation, the whole plane will look like this. Okay. So for instance, this point 1 and 1 will be mapped to this point, and this point 0, 2 will be mapped to this point. Okay, and 2, 0 will be mapped to somewhere here because I know it's just twice of this red vector. And this vector, what about this vector? Can you pause the video and then tell me where this green vector will be mapped to? So you can pause the video and then think about a moment and then tell me your answer, what your answer is. So now this green vector will be mapped to, because when you look at here, you know it's going to be -2 of the red vector plus the -1 of the blue vector. So correspondingly, in this new map, under the mapping, it should be somewhere here. Okay, should be somewhere here. So it should be -1 of the blue vector, which is this point, and then -2 of the red vector, which is this point. So it should be in the diagonal of these two vectors correspondingly. So this is the two-dimensional example. Just show you a couple examples. I think now it's time to take a look at problem 3. I know I spent 9 minutes to talk about those, still not yet gone to this problem, but I hope that you get some good idea on what the transformations do, geometrically speaking. So now take a look at the first vector in this case, which is A1, 0, 0 is the first vector, 0, 1, 0, second one, 0 vector on the third column. So how do you know what this matrix, what this transformation really does, so this is the way to look at it. So this is what you do. A times x. Okay, let's do a quick algebra. Oops. The next one is actually 0, 1, 0. And the very last one is 0, 0, 0 times x. It has to be 3 by 1. So let's say x1, x2, x3, arbitrary x. And then do the algebra. You can see that the first one is 1 times x1 plus 0 times x2 plus 0 times x3. You end up with x1, right? Similarly, x2, but the very last entry, it's going to be the third row times this column, because the third row is, they're all 0, so you get the 0 here. Now, what this does is, this is a 3 by 3, 3 by 3. So, and this is from R3, a vector from R3. And it maps this vector into, just keep, the result is to keep x1, x2, x1, x2, but ignore the x3. Geometrically speaking, this is what's happening. So let's look at a 3, x1, x2, x3. So if you have a point, so suppose this is the point, and this is the vector. This is the vector pointing to this one, and this is your coordinates x1. This is coordinates x2, and this is coordinates x3. So this vector has x1, x2, x3 as its coordinates. After the mapping, it's going to be like that. So where is that at? That's this vector. So it's on the x1, x2 plane, and then it's on this plane, on the x1, x2 plane. So basically, it's just the projection of this original vector onto the x1, x2 plane. So this actually is the projection onto x1, x2 plane, right? So this is what it does. Now take a look at the vector b. Vector bx, if you do the algebra here, times x1, x2, x3, you get x1, 0, and x3. So similarly, it's just a projection onto x1, x3 plane. Okay, so you can see what matrix does now. So this is the first example. Let's take